me begin with a word of prayer once I get up here. Dearly Father, we thank you for this day. Again, I thank you for this class and this morning. Just ask you to bless our work today and help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, let me start with an example here. So we've been talking about eigenvectors, of course, and talked a little bit about their application, right, to the problem of diagonalization. And I have told you guys it's not always possible to diagonalize a matrix, right? And there's a couple reasons for that. The one is that, well, it could be that all your eigenvalues are real, and despite the fact that all the eigenvalues are real, you just don't have enough eigenvectors. That can happen, right? When the algebraic multiplicity is larger than the geometric multiplicity, right? When the dimension of the eigenspaces are too small, that could happen. But the other thing that could happen to keep us from diagonalization in the real context is like we could have complex eigenvalues. So here's an example where that's going to happen. So let's look at how to calculate these kinds of things. So here it is. A is equal to minus 2, 8, minus 1, minus 10, 6, 1, 0, 0, 1. So our goal here is to find the eigenvalues. They might be complex. Well, they are going to be complex, all right? So same starting point as usual. We calculate the determinant of A minus lambda I, and that's the determinant of minus 2 minus lambda, 8, minus 1, minus 10, 6 minus lambda, 1, 0, 0, 1 minus lambda. Now this is very nice because we've got this block decomposition here, right? It's a block triangular in that sense. And so we can use property of the determinant that says this is actually the determinant of the upper block, minus 2 minus lambda, 8 minus 10, 6 minus lambda, times the determinant. I'm writing it this way, but it's kind of dumb. I mean, that's there's a determinant of a block diagonal matrix is the product of the determinants of the blocks. It just so happens that the block is 1 by 1 there, right? Anyway, what's this give me? Well, this gives me lambda minus 6 times lambda plus 2 plus 80, all times 1 minus lambda, right? By the way, you have a problem like this, you do not multiply the 1 minus lambda out, right? Why would you not do that? Why would you not multiply the 1 minus lambda out? What's our goal here? To find the zeros, right? If you got a factor, don't unfactor it. Leave it there. Just because you can do something doesn't mean you should, you know? So yes, we can all multiply, but do not multiply the 1 minus lambda through it. Leave it out there. It's where it needs to be. On the other hand, we will multiply this out, and we've got a lambda squared minus 4 lambda. That's a minus 12 plus an 80 is what? 68, right? Plus 68 here. Complete the square. We've got lambda minus 2 quantity squared plus 64 times 1 minus lambda, which, if you want, we could even factor. This is lambda minus 2 plus 8i times lambda minus 2 minus 8I. If you don't want to do it that way, you don't have to. The point is, you should be able to see that the determinant of a minus lambda I equals to 0 tells me that either lambda is equal to 1 or lambda is equal to 2 plus or minus 8I. All right? So those are my eigenvalues. One is real and one is obviously not, right? Just a reminder, when the eigenvalue is complex and the matrix is real, like this one, just a reminder, if we have, A times V is equal to lambda V, right? If I take the complex conjugate of that, you guys know what complex conjugate is? That means that every place there's an I, we replace it with minus I, right? So the way complex conjugate works is the complex conjugate of a product is the product of the complex conjugate. So like this is A star V star equals to lambda star V star. But if A is a real matrix like this is a real matrix, right? It's equal to its complex conjugate. So this is equal to A star. So my point to you guys here is simply that this gives me that A V star is equal to lambda star V star. See that? What that means is if I find the eigenvector for one of the complex eigenvalues, to find its eigenvector for the conjugate eigenvalue, all I have to do is complex conjugate my eigenvector. So it looks like I have 3 eigenvalues, but truth is I only have 2. One is real, one is complex. The one that's complex comes in a conjugate pair, so I don't really have to do it twice. I just have to do it once, and I can use the red calculation to do the rest. It's not a big deal. Okay, so let's do the easier one. Lambda equals to 1. What's my eigenvector? I'm looking for A minus I times U, let's say 1 equals to 0. That is what? Minus 3, 8, minus 1, minus 10, 5, 1, 0, 0, 0. All right. So I'll write it out as a matrix problem. Here's the augmented coefficient matrix, just to be sort of silly about it. So I can't just look at this and go, oh, okay, well, obviously this is my eigenvector, right? We've worked some problems in here where we could just guess the eigenvector. This is not one of them, I don't think. Right? So we actually have to work this out. This is the standard null space calculation that we did before. So what am I going to try to do? I'm trying to, find the reduced echelon form here. What should I do? I'm going to do is, I guess I'll actually write out what I'm doing. So I'm going to take row 2 minus 10/3 row 1. All right? Why would I do that? Mostly because of this, right? This last column is kind of dumb. I'm just writing it to emphasize what kind of thing we're doing. You don't really need to write that if you really understand properly. So my arithmetic here, if I subtract 10/3, that gives me a plus 3/10, right? Plus 10, actually. My bad. That gives me a plus 10, which cancels the minus 10 to give me that 0. What is 8? I'll write it down here. So we're looking also at 5 minus 10/3 of 8, right? For the next spot there. What's that? 15 minus 80 over 3, also known as, yeah, negative 65 thirds. That's what goes here, right? And how about the last one? We've got 1 minus 10 thirds of minus 1, right? That's for the last, the 2, 3 spot there. So that's what? 3 plus 10 over 3, also known as 13 thirds. All right. And of course the top one, not modified, so we still got the 8 and the minus 1 here, right? What is it? Something? Okay, so, oh, that's unpleasant. It is what it is, I suppose. All right, I'll go to my next step here, which is that this is equivalent to, I'm going to multiply through by 3 because I've got minus 3, 8, minus 1, 0. Hold on a second. Is 65 related to 13? Or 5 times 13 is 65?
I think so.
Okay, so I can divide that middle row by, basically, let me just say what I'm doing here. I'm going to do like row 2 divided by 13 thirds, right? And when I do that, that gives me a minus 5 here and a 1, which is much more pleasant than the one above, right? Then what? Okay, so I've done enough fractions for today. So let us do like 5 times row 1, and let's do 8 times row 2. All right, so I've got, minus 15, 40, minus 5. And I've got 0, minus 40, and 8. All right. Okay. Now, finally, I can add. Did I say that lambda equals 1 was going to be the easy one? I retract that claim. So row 2 plus row 1, yeah? Oh, my bad. I want row 1 plus row 2, actually, because we're trying to clear above the pivot position there. So I've got minus 15, 0, 3, 0, minus 40, 8, 0, 0, 0, 0, 0, 0. And we've come this far. Let's finish it. This is, I don't think we really need to finish it, but I'm this far in. I'm going to finish it. So 1, 0, minus 1/5, 0, 1, minus 1/5, I think. Is 8 over 40 1/5? Right? Now, so this tells me what? This tells me that U1 equal to, let's say, UVW, what's it actually equal to? Apparently, we have to have U equal to W over 5. And this one tells me V is equal to W over 5. So I can trade this for a W over 5, W over 5, and a W. Factor out the W. And you got 1/5, 1/5, 1, right? I say that this means we're going to choose U1 equal to what? Do we like, fractions are a mortal enemy, so we try to get rid of them when we can. So the way to get rid of a 5th is to make W equal to 5. Yeah, 5 seems like a good choice. So if we make W equal to 5, we've got 1, 1, 5. All right? In other words, the eigenspace with lambda equals to 1 is actually the span of this vector 1, 1, 5. Hopefully. Now, when you've gone through this much trouble to calculate an eigenvector, I think it's worth 30 seconds to check it, right? Let's check it. How do we check it? Let's try A times 1, 1, 5. What do we got there? Minus 3. Oh, my bad. Minus 2. Minus 2, 8. Well, actually, this is the dumb way to check it. The smarter way to check it is I want to check it on A minus I. I want to see if that actually does give me 0. That'd be easier to check that way. All right, so I'm checking minus 3. Although, if I made a mistake in setting up A minus I wouldn't detect that by doing this. That is one downside of my current check, but the upside is that it's easier to check. Because if something's 0, it's easy enough to see. If it's not 0, well, it should be readily apparent. Moment of truth here. So I get minus 3 plus 8 minus 5 for my first one. Then I get minus 10 plus 5 plus 5 for my second one, and I get 0 for my third one. This is also known as right? So we can check our answer. Yeah. So there you go. It is in fact an eigenvector with eigenvalue 1, as claimed. Now what? Next up, let us calculate the complex eigenvector, right? So let's move on to that part of the calculation here. So we've got lambda 2, let's say, equal to 2 plus 8i. So we're going to look at a minus parentheses 2 plus 8i. That times my u2 vector equal to 0, right? So let's see here. What is that? Let's think through it. A minus, that gives me a minus 4 minus 8i for that component. Should have worn my glasses today. 0. And let's see here. Next up, we've got that 8 up there. I've got 6. 6 minus 2 is 4. The imaginary part's still minus 8i. All right. 0 down here. And then finally, minus 1, 1. And okay, so down here, I'm doing 1. This one is going to be 1 minus parentheses 2 plus 8i, right? Which gives me minus 1 minus 8i. All right. That times u v w. I want that to be equal to 0, right? All right, so first of all, we can treat this as a 3-by-3 problem, but I don't think that's really necessary, is it? Because if we look at this last row here, right? We can immediately read from that minus 1 minus 8i, right, times w is equal to 0. So therefore w is equal to 0. If you can see some kind of low-hanging fruit like that with a 3-by-3 problem, use it. Now we have a 2-by-2 problem, right? Because what we're really up against is minus 4 minus 8i, 8, and minus 10, 4 minus 8i, right? 0, 0. because that's what I get from just looking at this, right? And that's reasonable because we know W is equal to 0 for this system, right? So the minus 1 and the 1 at the end of those equations doesn't contribute anything. We can just focus on this, yeah? And also, I would point out that, well, let's just clean this up a little bit. If I divide by 2, this is what? This is minus 2, minus 4i, 4, minus 5, 2, minus 4i, right? If I can, I mean, if you trust yourself, you know you can just ignore one of the equations and solve the other, because it must be the case that there's infinitely many solutions here, right? The theory says that there's at least one complex eigenvector, which means it is an inevitability that these equations are the same equation. But to check our calculations, it would be healthy for us to verify that the top equation and the bottom equation here are actually the same equation, right? So how do I get from, you know, if we look at this one, this is what? This is like 4 times what? Minus I, right? Plus 1/2. That's what this is, yeah? So because of that, in order to get from the top equation to the bottom equation, apparently I must multiply by minus I plus 1/2. That must be the case. If that's how this one goes to that one, it must be the same multiple up there in order for them to actually be the same equation, just multiplied by a complex scalar. So let's check that out. Minus 2 minus 4i. This is just a consistency check, so this isn't actually necessary to find the answer. I'm just hedging my bets here, guys. So this, when I multiply this out, I get 2i, and then minus 1, and then plus 4i squared, and then minus 2i. The 2i's, they be canceling, and that gives me minus 1 minus 4, also known as minus 5. Hey, there you go. So indeed, if we take the top equation and we multiply by minus I plus 1/2, we get the bottom equation. So these are the same equation. So to solve this pair of complex equations, we could pick either one. All right, either one will give us the solution set. I personally like the top equation, I think. Yeah. So I'll pick this one. Just use this one right here. All right. So that tells me that minus 2 minus 4i times u plus 4 times v equals to 0. Let me use a marker we can actually see. Okay, so I'm going to solve for v. V is equal to 2 plus 4i divided by 4 times u. Let me clean up the fraction there. That's 1 plus 2i divided by 2 times u. All right. So what does this give us? This tells me that u2, which I'm calling a u, a v, a w. Remember, we have previously argued that w is 0, so that's done, right? And then I've got u up here. I've got, and then, 1 plus 2i over 2 times u, right? This, for u, not equal to 0, gives, eigenvector with lambda equal to, what was it? 2 plus 8i, all right? Yeah. Thank you for the assist. Now, u can't be what? U can't be 0. What could u be though? 2? Yeah, we could pick u equals to 2, or u is any element of the complex numbers without 0. This is what's so annoying as a grader about these problems. There is an infinity of possible complex eigenvalue vectors, and they don't have to look at all the same. Because this is a complex scalar. I could put 3 plus 4i there if I just wanted to mess with the instructor. Don't do this. do u equals 2, please, for the sake of my... Well, I mean, I'm going to give you the points back when you talk to me after the test. You know, but in the meantime, you'll be worried. So, and I mean, you might be satisfied with yourself because you know you're right, and you just, you know, basically did a mathematical prank on me by choosing something so absurd as u equals to 3 plus 4i. But, you know, it would be much nicer just to pick u equal to 2 to have the answer that everybody else got. Because math is nothing if not consensus, right? All truth is determined by consensus, right? Don't agree with that. All right. That turned out very badly for us about 5 years ago. Anyway. I guess you guys were young enough at that time to not be responsible for not rebelling. My generation, on the other hand, shame on us. Okay, so what was I doing? So now we have the complex eigenvector. So let's choose u equal to 2 for the sake of specificity. u2 equals to 2, 1 plus 2i, and then 0. All right. So by the red comment, u2 conjugate, which is going to give us actually 2, 1 minus 2i, 0, has lambda equals to 2 minus 8i. All right. I'll call that 3. I'll call this u2, lambda 2. All right, so I don't need to do any further calculations. That's the complex eigenvector with conjugate eigenvalue, you know, 2 minus 8i. Any questions? Yeah.
I'm just slower when I was writing something, so I was exactly
That's fine.
What was the arrow, the negative I plus 1/2 by the matrix in the middle?
It's right here? Oh yeah, that's I'm going down here. This is v. See, I got v equals to that. So that's the middle equation. So I've got 1 plus 2i over 2. So just putting this right here is going up here. And then what I was saying after that was that we can make u any complex scalar, like any non-zero complex scalar would work here to give an eigenvector. So like the answers could look very different if instead of using u equals to 2, we used like, you know, for example, if I did my u equals to 3 plus 4i, because I'm weird, I would have, let's get rid of the half at least. Let me allow me that much. 6 plus 8i, there we go. If I did that, then I'd have u2 equal to, you know, like 6 plus 8i. 1 plus 2i times 3 plus 4i, 0. You know, that would have been my eigenvector. And still the complex conjugate of that would be an eigenvector for, you know, 2 minus 8i. All right, so what else were we doing in here? We weren't just finding eigenvectors and eigenvalues. We were doing things with these, right? Which was what? Solving differential equations, right? So if we ask ourselves, a couple different questions. The one is the diagonalization question, right? So if I let beta equal to, let's say, my, what was it, 115? And then I let my next vector be u2, which I'm going to go back to the easier one, 2, 1 plus 2i, 0. And then I've got my 1 minus 2i, 0, right? If I let that, if I use this complex basis, all right, and then if I was to look at beta inverse A beta, what would I get? Well, I would get eigenvalue 1, and then minus 2 plus 8i, and then minus, what's the oh yeah, 2 plus 8i rather, and then 2 minus 8i. So this matrix is not diagonalizable. So this makes A is so-called complex diagonalizable. Which in most people's book would mean it's not diagonalizable because most people want to keep it real. All right? What that means is that if you have a system that involves this matrix, it is fundamentally different in the nature of its solution than one which is real diagonalizable. So like, if we go to one of the standard applications we look at in here, which was, to solve the, we can solve the system, right? So application, if I'm solving dr dt equals to AR. So on the one hand, from lambda equals to 1, we have the thing we've already talked about. We get a solution, let's say R1, which is of the form e to the lambda t times u1, which in this case would just be e to the t times my 1, 1, 5 vector. Okay, that's one of my solutions, all right, to the differential equation dr dt equals to AR, where R is a vector of, let's say, x, y, and z. All right. On the flip side, this one, if I have my complex eigenvalue, 2 plus 8i, I get, let's say, z, a complex vector solution, I get z e to the 2 plus 8i times t times my, where was it? Times my u2 vector, all right? And just to be explicit here, guys, the way this works is this is e to the 2t times cosine of 8t plus I times the sine of 8t. So here I'm using the so-called imaginary exponential. Like there's a general result, guys. If I have e to the I theta, that gives me like cosine theta plus I times the sine of theta. So this is, something to know about. And also, if I have e to the 2 plus 8it, the laws of exponents work. So like what I'm doing here is e to the 2 plus 8it is equal to e to the 2t plus 8it, which is equal to e to the 2t times e to the 8it. And then what I did is just to put theta equals to 8t there, okay? So this is Euler's formula. This is the imaginary exponential. Now the u2, I've not written yet. Let me write that out. I'm going to put some big parentheses here. And I'm going to take u2 and I'm going to write it in a way which forecasts the next calculation. Namely that we're going to want to look at the real and the imaginary parts of the solution. So here, my u2 was, the real part of u2 is 2, 1, 0. See that? That's the real part of the complex vector. And then I do plus I times 0 minus 2, 0. Do you guys follow? What have I done here? So I've taken the complex vector, right? And, oh man, I picked the wrong one. I'm sorry. I was looking at this accidentally. I should have been looking at that. What's the difference? I got a sign error there, right? This is 2, 1, 0. plus I times 0, 2, 0, right? So it's not supposed to have a minus 2 here, but a plus 2, because we're working with the eigenvalue 2 plus 8i. Right? Now the problem at the moment, as far as solving that differential equation, is this is not a real solution, right? Because it's got I in it. This is a complex solution. So to find the real solution, the beautiful thing is that if you have z is equal to, like, let's say x vector plus I times y vector, then dz dt is equal to dx dt plus I times dy dt. But if that's also equal to a times z, which is, by the way, a times x plus iy, well, that's equal to ax vector plus I times ay vector. And in order for dz dt, so basically I'm telling you here, guys, is the fact that dz dt is equal to a times z separately gives us that dx dt is equal to ax, and also that dy dt is equal to ay, which means that separately the real and the imaginary parts of the complex solution are actually solutions to the differential equation, because it's linear. So all we have to do then to write down the solution is to calculate what's the real part and the imaginary part of the complex vector z. And so that is just a short calculation, which I'll do here, which is e to the 2t cosine 8t times the vector 2, 1, 0 minus the sine of 8t times the vector 0, 2, 0. Parentheses, plus I times e to the 2t, big parentheses, sine of 8t times the 2, 1, 0 vector, plus cosine of 8t times the 0, 2, 0 vector. So I'll finish the solution here. So my solution then, in general, for this 3 by 3 system of differential equations is c1 e to the t times my 115 eigenvector with eigenvalue 1 plus c2 e to the 2t. Could I not write all that again, if you guys don't mind? Let me save myself the trouble of writing all that again. Let me use some labeling here. So this piece right here is the real part of the complex solution, z. And not including the I, guys, all right? Not including the I. This is the so-called imaginary part of z. Now, common confusion, guys, is that people think, well, it's the imaginary part. That means you're putting the imaginary number in it. Well, that's not true. The imaginary part of a complex solution is itself real. Just like the imaginary part of a complex number is real. Like, what's the imaginary part of 3 plus 4i? Four. Right, it's 4. As you can see, that's a real number. Same thing here, but there you go. This is the general solution to the differential equation, which I'll write out in gory detail somewhere. Somewhere. Let me show you what we just solved. I need to squeeze it in here somewhere. I guess I'll put it here. All right. My original matrix A was, oh man, I really need glasses now. Just tell me the top row in that thing.
Where?
The original matrix A here.
-8, -1.
Okay, what's the second row?
-10, 6, 1.
And the last one is just 0, 0, 1. So guys, we just solved this system of differential equations. Dx dt is minus 2x minus 8y minus z, and dy dt is minus 10x plus 6y plus z, dz dt equal to z. This system of three differential equations has that solution. Here, the R is just a notation for, x, y, z. All right? I allow you guys a formula card for the next test, right? Seems like the formula for how to find the real and the imaginary part of a complex solution might be a smart thing to put on there, right? Because you guys aren't like super comfortable with what I just did, right? But there's just a formula, really. It's not, it may look complicated at the moment, but it's really not. The reason there's a minus here is why. That was from I times I. I times I is I squared is minus 1. That's where that minus 1 came from. Cosine times that is where this came from. And then you've got cosine times the I, which is this term. And you've got sine times the 210, which is that term. And the I just factors out. It's just that. And the mathematics, which told us that e to the lambda t times u was a solution, equally well applies to show you that e to the lambda t times u is still a solution in the case that lambda is complex and u is complex. The same calculus holds for complex valued functions of a real variable. Okay, so I wanted to take time to do a slightly more complicated example. I think I've achieved my goal. Any questions? So the one sort of remaining application that I want to talk about with you guys. So first of all, before test 2, we are not going to settle the question of the general question of what happens when the matrix is not diagonalizable. That question looms and remains after test 2. So on test 2, I would simply test you on your ability to calculate eigenvectors and to use the theory we've been talking about, namely to solve the differential equation problem, to diagonalize a matrix, to calculate a power of the matrix like we looked at last class, right? We saw we could calculate the nth power of a diagonalizable matrix. There's a few other applications that I should tell you guys about. One of those is important because, actually it's really important, and it kind of gets shortchanged in your education, but not entirely though. How many of you guys have had discrete math, like 250? Okay, so you guys have suffered the indignity of difference equations, right? No? The difference equations, have that happened yet? Like you have a sub k plus 2 defined by a sub k, and no, a sub k is defined by like a sub k minus 1 and a sub k minus 2, these sorts of recursively defined problems. That may be later in the course. Like I have not taught 250, so I don't know when that hits you. I'm told that Math 250 lulls you into a sense of complacency. It's like, this is easy, this is easy. And then all of a sudden, about this time in the semester, the difference equations descend upon you. And it's like, oh, there's actually something to think about here. Comparatively speaking, there are these things called, I'm pretty sure difference equations are in there. You know what, I may be talking about Math 350. That may be my mistake. But anyway, the other problem besides just a differential equation we can think about is a problem where we have like a state vector, all right? We could call that, let's say, the, x sub 0, all right? And then we've got some physical system that we can describe by A. And then that gets us to, a times x sub 0. That gets me the next state. So that's like my next state, x sub 1, right? And then I have some physical process that happens, and it's described by this same matrix A, and that gets me to a times x1. So my second state after the zeroth, like the zero state, first state, second state, like this, all right? And so forth and so on. So like this is recursively defined. The kth state of the system is A times the k minus 1th state of the system, right? This is a recursive definition. The next step is defined in terms of the previous step. if you have a system like this, there's a significance to an eigenvector. There's going to be an eigenvector to this problem. Think about this. What happens is you take the limit as k goes to infinity in such a problem. What's the deal here? If that limit exists, what would happen? Does the limit satisfy like linearity rules? It does, right? So if you think about that, what that means is you can pull a limit outside of a matrix multiplication, provided that the limit of the vector exists, right? So this would be like a times the limit, because this matrix is constant, guys, okay? So if this, and let's call this thing x sub star for lack of imagination, all right? Supposing that this limit exists, call it x sub star. What's the limit as k goes to infinity of x sub k minus 1? Would that have a different limit? No, that would also be x sub star, right? Okay, great. What does this mean? This means that a times x sub star is equal to x sub star, right? So this is also called the steady state solution for such a problem. What is the steady state solution then? Is it an eigenvector? If so, what's its eigenvalue? What's this say? Lambda equals to what? What's that?
A equals the identity matrix?
Oh, okay. Well, I mean, yeah, I mean, we could rewrite this as A minus the identity matrix times x star equals to 0. I guess we've been doing that more lately, right? But what is the lambda? What's the eigenvalue? I heard a 1. Yeah, the eigenvalue is 1. Indeed, the eigenvalue is 1. So if we have such a system, the significance of the eigenvector problem is it gives us the steady state solution to a problem like this. Let's see if I have time to show you that. Oh, rats. Well, I'll show you next time. But so, for example, there's something called a stochastic matrix. A stochastic matrix is like a matrix of, it could be, for example, a matrix of like birth rates and death rates. And your vector might be like a population vector where the first component is mice and the second component's tigers, you know? Now let's make this more positive. Like the first component's the number of cats and the second component is like steamrollers. And you could have like a 2x2 matrix that has to do with the birth rate and the death rate of steamrollers versus the birth rate and the death rate of cats. And then ideally, like if the system was set up correctly, the limiting vector should have 0 cats and a finite number of steamrollers, I guess. But, sorry. I'll stop. So we'll do that kind of thing Friday. Not necessarily the cats and the steamrollers, but hopefully the difference equations. So.